Hi, and welcome back to AWS Julie. Today we are continuing our new series covering network fundamentals in AWS, and we will cover the second layer of the OSI model, Layer 2, the data link layer. Please remember to share this video with anyone who may be interested. Give it a thumbs up if you like it, sub if you love it, and let's dive in. So we're diving deep into the OSI model, and we are learning about Layer 2, the data link layer, which is, in my opinion, the most important layer of the OSI model because all of the layers above Layer 2 rely on the device-to-device communication provided by the data link layer. And our data link layer runs on top of Layer 1, the physical layer. And Layer 2, the data link layer, requires a functional Layer 1 network to operate. Higher layers of the OSI model build on top of the lower layers and add additional capabilities and features to the layers as it builds. Layer 2 can run on different types of Layer 1 networks. Remember, those are copper, fiber, radio frequency, and those provide the same capabilities. Since we're covering foundations, let's focus on Layer 2 using Ethernet, but know there are different capabilities and standards for the data link layer. Most local networks use Ethernet. Layer 1 defines, remember, specifications for the physical wavelengths and voltage, but Layer 2 introduces frames. Frames are simply a format for sending information, sending data over our Layer 2 network. Layer 2 also introduces to the network a unique hardware address known as the MAC address for all of your devices on your network. Hardware MAC addresses are hexadecimal addresses that are 48 bits long. And an important distinction for MAC addresses is that they are not software assigned addresses. It is a unique address attached to a piece of hardware. MAC addresses are formed of two parts: the Organizational Unique Identifier, or OUI, which is assigned to organizations or companies that manufacture network devices, and the Network Interface Controller, or NIC. These two parts make up the MAC address, and all MAC addresses for network cards should be globally unique. So the Ethernet frame on the data link layer uses Layer 1 and is transmitted on Layer 1's shared physical medium, and it's converted to voltages, radio frequencies, or light, and it is sent across the shared connection and is received by other devices on our network. So Layer 2 provides frames, and Layer 1 handles the physical transmission and reception of data. So let's take a step back and let's dive into frames. Frames at Layer 2 act like a container and contain different components. The first part of the frame is the preamble and the start frame delimiter, and this allows devices to know that this is the start of the frame. Next, we have the destination MAC address, and this allows frames to be sent to a specific device on the network or all FFFs, which sends the frames as a broadcast. Next, we have our source MAC address, and this is the device that is transmitting the frame, and this allows us to receive replies. Up next, we have the ether type, which is commonly used to specify the Layer 3 protocol that is putting its data into this frame. And we're going to talk about this in the next lesson, but Layer 3 uses Layer 2 frames to transmit data to the device. And these three fields are the MAC header, which controls the frame destination, specifies the source, and also the function. Next is the payload, which is 46 to 1500 bytes in size for a standard frame. The payload is the data the frame carries from the source to the destination. It is generally provided by Layer 3 of the OSI model, and the ether type defines which Layer 3 protocol is being used. So maybe in this case, we're using the IP protocol. And again, we're going to talk about this in the next lesson, but this process is called encapsulation. It is data that is generally from Layer 3, maybe an IP packet, and it is put inside an Ethernet frame. It is encapsulated in this frame, and the frame delivers the data to a different Layer 2 destination where the frame can be analyzed and the Layer 3 payload can be extracted. And of course, there are more parts of a frame, but we are focusing on the main parts for the fundamentals. And the last part I want to cover is the end of the frame, which is the frame check sequence. And this is used to identify any errors in this frame. The frame check sequence is a cyclical redundancy check, so a CRC, which is an error detecting code commonly used in digital networks and storage devices to detect accidental changes to the raw data. A CRC check allows the destination to check if any corruption has occurred. Another important part of Layer 2 is that it allows controlled access to the physical medium of Layer 1. And remember, this was a limitation of Layer 1. The Layer 1 software running on your network card will transmit the data received onto the physical median, but Layer 2 adds controlled access to that physical median. So let's look at how two laptops on our network communicate. Let's say that laptop A wants to communicate to laptop B using Ethernet as the shared physical medium and using a Layer 2 network. To begin, Layer 2 creates an Ethernet frame containing the data or payload that laptop A wants to send to laptop B. And this is great because Layer 2 allows us to send a payload to a specific MAC address, and Layer 2 can use the physical layer, Layer 1, to transmit that data. Next, Layer 2 is going to check with Layer 1 and search for any signs of a carrier signal on the physical medium. And for the Layer 2 network, if another device on the network was transmitting a packet, Layer 2 would see that carrier signal on the network. So Layer 2 is looking for a carrier to send its payload. And this is the job of a Carrier Send Multiple Access, CSMA. This is how Layer 2 controls access to the physical layer. If it does not see a carrier signal, Layer 2 will pass the frame to Layer 1 and convert the data frame to the physical standards for Layer 1 network. And remember, Layer 1 does not understand what the frame is, it only sees the data. And it's going to transmit that data onto Layer 1, the shared medium. So for the destination MAC address or laptop, the Layer 1 receives this raw data and passes that frame up to that device on the Layer 2 network. And at this point, Layer 2 will receive the destination MAC address of the frame, and it's going to see that it's actually destined for itself, and then it'll pass that data or payload to laptop B. Now, if laptop A is transmitting its frame of data and laptop B also wants to transmit data at the same time, laptop B will check for a carrier signal and will see one because laptop B is transmitting a frame. At this point, laptop B will wait until a carrier signal is not detected. Layer 2 adds this access control. Layer 1 does not have this access control, and remember, it can receive collisions when data is being sent simultaneously. However, sometimes collisions do happen at Layer 2, and Layer 2 does contain collision detection. If a collision is detected at Layer 2, both devices will stop transmitting for a random period of time and then try again. A jam signal is sent with a random backoff, which is a period of time where no device will attempt transmission. If another collision occurs, the random backoff time is then increased. Remember, in your local network, your laptops, your mobile phone, your tablet, they're all connected using a network hub, which is a Layer 1 device. And since hubs are Layer 1 devices, they do not understand frames. And when a laptop, let's say laptop A, sends data to laptop B, that data is going to be sent to all devices on our network. Network hubs broadcast packets to all devices, but the devices know that the data packet is not destined for them, and then they can discard that packet. But when collisions occur, all ports for the hub are going to also receive a collision even though you're running a Layer 2 network because the hub is a Layer 1 and does not understand Layer 2. To reduce the collisions along with the improvements of CSMA, you can replace your network hub with a network switch. A network switch is a Layer 3 device and it works the same as a hub, but it understands Layer 2. Using a network switch allows each of our devices on the network to have its own hardware address, the MAC address. And as a Layer 2 device, a switch has Layer 2 software running and maintains a MAC address table. And over time, switches will learn what is connected to each port. So switches understand frames and MAC addresses, and it maintains a MAC address table. And this table will start off empty, but as the switch receives frames on its ports, the switch learns which devices are connected to which ports, and then will populate that MAC address table. So if laptop A sends a frame to laptop B, when that frame arrives to the switch, The switch will know the correct port for laptop B and will send that frame to laptop B. But if it does not know the port, it will send the frame to all ports and then update its table. Switches store and forward frames based on the MAC table and then will discard those frames. They interpret the frame and make decisions based on the source and destination MAC addresses. And this intelligence helps to reduce collisions because it's not going to forward those collisions to every device. Each port on the switch is a separate collision domain so that only two things can transmit at the same time are the device and the port it's being connected to. So if a collision occurs, it's going to be limited to that one point. Layer 2 adds identifiable devices, media access control, and collision detection to Layer 1. This allows unicast one-to-one communications and broadcast one-to-all communications. Now in the next lesson, we're going to dive into Layer 3, the network layer, and we're going to build on top of Layer 2 that we just discussed in this lesson. Thanks so much for stopping by, and I hope to see y'all again real soon.